So far, we have already discussed about the damped mechanical oscillator. In this class, we will learn about the damped electrical oscillator. Let us consider that there is a LCR circuit in which the capacitor C is LCR circuit in which the dissipation of energy across in the resistance of the circuit. Here we are looking in figure first, which may be dissipated in the connecting wires and the inductor. Let the capacitor is charged to a certain value Q naught and is then allowed to discharge through the resistor and inductor. Let the induct let the instantaneous current in the circuit be I, then the induced EMF in the inductor is L di upon dt. The potential drop across the resistor is Ri, and if Q be the instantaneous charge on the capacitor, then potential drop across it will be Q by C. Applying Kirchhoff's law, we have the equation L di upon dt plus Ri plus Q by C is equal to 0. This is the equation number 1. Now I is equal to dq by dt, rate of uh, flow of charge. Therefore, the above equation becomes L d2 q upon dt square plus R dq by dt plus q by C is equal to 0, और डिवाइड कर देंगे एल से, तो डी टू क्यू अपॉन डी टी स्क्वायर प्लस आर बाई एल डी क्यू बाई डी टी प्लस 1/LC is equal to 0. Equation number 3. This is the equation for the simple harmonic oscillator to the electric oscillator. Here the oscillator variable is Q and the damping factor is proportional to dq by dt. R is the damping constant and represents the overall resistance of the circuit. Putting R by L is equal to 2B and 1 by LC is equal to omega naught square, we have d2q upon dt square plus 2b dq by dt plus omega naught square q is equal to 0. The solution of the equation is q is equal to e to the power minus bt, a1 e to the power b square minus omega naught square t plus a2 minus under root b square minus omega naught square t. This is the equation number 5, where a1 and a2 will have the dimensions of charge and their values will depend upon the initial conditions of the oscillator. Here again, damping, here again, depending upon the value of under root b square minus omega naught square, three cases arises. Case first, heavily damped oscillations. This is the figure, this is the heavily damped oscillations, only no, there is no oscillations, and this is the critically damped oscillations, long time taken, and this is the lightly damped oscillations, these variables with time and lightly damped oscillation. So first is heavily damped oscillation. Oscillator is said to be heavily damped if B square is greater than omega naught square or R square by 4L square is greater than 1 by LC. The charge on the capacitor decays to 0 in the minimum possible time. Case second, critically damped oscillations. When b square is equal to omega naught square or r square by 4l square is equal to 1 by lc, this discharge is non-oscillatory. The charge at any instant t is given by k is equal to e to the power minus bt into a plus bt. Here a has the dimension of charge and b has the dimension of current. The rate of decay of charge depends upon the damping constant. The behavior of the oscillator is said to be dead beat. इसको हम लोग dead beat के नाम से जानते हैं. Case third, lightly damped oscillations when b square is less than omega naught square or r square by 4l square is less than 1 by lc. The discharge is oscillatory and the charge at any instant is given by q is equal to a naught e to the power minus bt cos omega naught dot t minus phi, or q is equal to a naught e to the power minus r by 2lt cos 1 by lc minus r square by 4l square half plus half t minus phi. The frequency of the damped oscillations is given by frequency इसकी हो जाएगी f naught dot is equal to omega naught dot by 2 pi is equal to 1 by 2 pi under root omega naught whole square minus whole omega naught square minus v square, or f naught dot is equal to 1 by 2 pi under root 1 by lc minus r square by 4l square. Thank you for watching the video.